equals x minus 2 times e to the negative x power. We want to analyze this function and sketch the graph of it. So there's a lot of stuff going on here. I'll take you step by step. First, we analyze just the function itself. We can find domain, and there's no discontinuities, no place where this function can be undefined. We're not dividing by anything. So our domain is negative infinity to positive infinity. Then we can find our x and y intercepts. So the x-intercepts is where y is equal to 0. So we set our function equal to 0. And e to the negative x will never be 0. It's always positive. So we don't really have to worry about this term. We're just concerned with the x minus 2, which gives us our x-intercept at x equals 2. So that's our point for that. Our y-intercept is our x equal to 0. So when you plug that into our original function, anything to the 0 power is just 1. 0 minus 2 is negative 2. So our y-intercept is 0, negative 2. Now to find if we have any horizontal asymptotes and our end behavior. So the limit as x approaches infinity of x minus 2 times e to the negative x. Well, if you take infinity minus 2, still going to be infinity. And if you take e to the negative infinity power, that's just like saying 1 over e to the infinity power, which brings us really close to 0 as we're going there. So we're left with infinity times 0 equaling 0. And as we go to negative infinity minus 2, still going to be negative infinity. E to the opposite of negative infinity, be e to the infinity power, should be infinity. Negative infinity times positive infinity equals negative infinity. And then we have to find where our function is positive or negative, so above or below the x-axis. So we found our x-intercept is 2. So from there we can determine if the function will go, if it's positive, it'll be above. If it's negative, it'll be below. So we know that e to the negative x is always positive, and pick some values below and above 2, 0 and 10 to make it easy. 0 minus 2 will give us a negative number. 10 minus 2 will give us a positive number. If you multiply these two factors together, we're left with negative on the interval from negative infinity to 2, and positive on the interval 2 to positive infinity. And that's all we can tell from our original function. So we can move on to the derivative. So we have a product rule here, and when you take the first derivative of this, you get the first x minus 2 times the second term, e to the negative x power. It's a chain on the negative 1. And then we get the second term times the derivative of the first term, which is 1. And here, after you distribute, you get an e to the negative x in every term. So you can pull that out, and we're left with y prime being e to the negative x times negative x plus 3. Here's where we can find our critical numbers. Critical numbers are y prime equaling 0 or y prime not existing. But our domain is everywhere, so there's no place where y prime doesn't exist. We don't have to worry about that. Just have to worry about where y prime equals 0. So again, we set our function equal to 0, and Again, this is never going to be 0, always positive. We're only worried about the negative x plus 3. So we set that equal to 0, and we get x equals 3. Put that on our number line here. We want to find where the function is increasing or decreasing. So it'll always be positive here. Oh, and plug 3 in, pick 2 numbers around it to test them in our functions here. So this will be positive both times. If you take 0 plus 3, it's positive. Negative 10 plus 3 is negative. Multiply these two factors together, because that's what we're observing here. You get positive and a negative, so increasing and decreasing. And because we're going from increasing to decreasing, we have a local max at the point 3. Since we're going to graph this, we might as well evaluate for it. So the local max is at 3 e to the negative 3rd power. So that's what we can find from our derivative. If you take the second derivative here, I made it a little simpler because we're running out of room on my poster board. So we get negative e to the negative x power times x plus 2. Same process as this, basically. Couple different numbers. So to find our concavity, we set y double prime equal to 0. And when you plug that in, again, you're not worried about this term, only worried about x plus 2. When x plus 2 equals 0, x equals negative 2. We plug that into our number line. So this term, positive e to the negative x power, is always positive, and then you just take the opposite of that. So this term will always be negative. And picking numbers below and above negative 2, negative 10 plus 2 gives me a negative number. There we go. And 0 plus 2 gives me a positive number. Since we're multiplying these terms again, we get positive, negative. So on the interval from negative infinity to negative 2, we're concave up. And on the interval negative 2 to infinity, we're concave down. Since we're changing concavity here, we have a point of inflection at negative 2. And when you evaluate negative 2 in our original function, you get the point negative 2, comma, negative 4e squared. Now the graph of this is on a very narrow spot. And I graphed it previously. So let's see here. If you can see that. I started at negative 2, because that's where, well, a little before negative 2, that's where our graph changes concavity, so there's a little something going on before that. But most of it, the bulk of the interesting part of our graph is between 0 and 4, really. So we are increasing concave up. The rest of the graph we're concave down. Increasing until we hit 2. Increasing until we hit 3. Decreasing the rest of the way. And we are negative from 0 to 2, our x-intercept, and positive 2 to infinity.